Okay, so let's first review what we did in the lab, right? The goal, right? Whenever we're doing stuff, we should think all the time about what our end goal is too, right? So we want to know how much energy there is per gram in our food, whatever that food was, right? So peanuts have lots of protein, lots of oil, some sugar, all that kind of stuff, right? So we want to know how much energy is in that food. So your body burns it. Now, physically burning it and burning it up with enzymes, stuff, it's a different pathway. But like we talked about with our catalysts and stuff, you start in the same place, end in the same place, your delta H, your change in reaction energy is going to be the same. So I don't care if I actually burn it or if I eat it and burn it up with enzymes, I turn it into carbon dioxide and water. This turns it into carbon dioxide and water. So we're going to get the same change in energy. So if what I want is calories or joules per gram of our peanut, or I think I'll buy cashews actually, so in case somebody has a peanut allergy, I need to know the mass of this peanut. So that's the first mass we're going to use. And that can be confusing because we have a second mass also. One of the reasons Mr. Fredrickson is always grumping at you to not only label things, but label things grams water, grams peanut, grams whatever, right? So let's say we got 2.23 grams of our peanut, right? Who knows, right? Whatever our cashew was, or Cheeto or marshmallow or whatever it is that you're burning on that. So I need to know the energy that gets released by that. So the new equation that we've got is that Q equals MC delta T for heating things up. So we burned the peanut, but that heated up the water, right? It took the water from being room temperature, somewhere in the neighborhood of 20 degrees Celsius, up to some temperature higher than that. Let's say it went up to 35 degrees Celsius. So if you look on the directions, it says to record the temperature until it starts coming back down again. We're not going to have trapped all the heat, but the heat that we did trap all will go into this temperature change. So if we went from 20 to 35, our delta T, that triangle, that doesn't look like a triangle, that delta T is change in temperature. So if I record my highest minus my initial temperature, that'll give me my change in temperature. I just made up 15 degrees. The specific heat, the stuff that's heating up is the water. Now the can is heating up too, and we're not including that. So we know right there we have some error, right? But we're going to include just the can, which is water, and that's got a specific heat of 1 calorie per gram degree Celsius, right? And then the mass of water, which we record. Now I told you to get 100 milliliters of water. So your mass should be around 100. Right? Because the density of water is 1, but you very likely did not measure exactly 100, and you certainly didn't get 100.00. So you should use the mass you actually got, which is probably going to be something like 98.5 or something, right? Grams of water. Hopefully you're fairly close to 100 there, but it will not, don't just write 100, right? Go off of what you did actually mass. So we multiply those together and get our value. And I am too lazy to do that in my head. So I'll multiply those three together and I will show that calculation, 98.4 grams times 1 calorie per gram degree Celsius. It is not that for everything in the world. It is that for water. Everything heats up and cools off differently, right? Like we saw when we were first learning about this equation, times 15 degrees Celsius. So 98.4 times 1 times 15 is going to give us 1476 little c calories is our Q. The energy that the cashew lost is the energy that the water gained, right? However much energy this lost is how much energy the water gained. Not really, we lost some along the way, but that's all we can account for. So when you're doing the second version of this, you should try and maybe lose less energy. See if you can think of anything that you can modify to try and lose less of the energy, because you're going to have lost quite a bit, really. Historically, you get about 50% or so, usually with this standard setup. So now I'm going to do this, but this is in little c calories. Really, food calories or kilocalories is divided by 1,000, so that's 1.476. Just like going from meters to kilometers, I move my decimal point 1, 2, 3 places. So I'm going to move my decimal point, and we can get our calories per gram, right? That's my estimates were real low. It should be much higher than that. But anyway, so we do 1.476 divided by 2.23, and that would give us our calories per gram of 0.66 calories per gram. And if you look up cashews, they would be way more than that. But I just made up numbers because who cares, right? Hopefully that helps on those calculations. The main thing is keeping track of which mass we're talking about where, and that you were heating up water, so you use water-specific heat, right? Anyway, that's that.